The short electric dipole. Any linear antenna may be considered as consisting of a large number of very short conductors connected in series. A short linear conductor is often called a short dipole. A short dipole is always of finite length. Let us consider a short dipole as shown in figure. A short dipole antenna has a length L is very short compared to the wavelength. Plates at the ends of the dipole provide capacitive loading. The short length and the presence of these plates result in a uniform current I along the entire length L of the dipole. The dipole is energized by a balanced transmission line. It is assumed that the transmission line does not radiate and therefore its presence is disregarded. Radiation from the end plates is also considered to be negligible. The diameter D of the dipole is small compared to its length. Thus, we may consider that the short dipole appears as in figure B. Here it consists a thin conductor of length L with a uniform current I and point charges Q at the ends. The current and charge are related by dq by dt is equal to I. The fields of a short dipole. Let the dipole of length L be placed coincident with the z-axis and with its center at the origin as shown in figure. The fields from the dipole have only three components: Er, E theta and E phi. It is assumed that the medium surrounding the dipole is air or vacuum. If a current is flowing in the short dipole, the effect of the current is not felt instantaneously at the point P, but only after an interval equal to the time required for the disturbance to propagate over the distance r. Instead of writing the I, the current along the dipole is I naught e to power j omega t, which implies instantaneous propagation of the effect of the current. The propagation time as done by Lorentz, and we can write it as I is equal to I naught e to power j omega t minus r by c. Where I is retarded current, R by C results in a phase retardation, which is equal to 2 pi f into r divided by c radians, that is 360 degree, into FR by C, which is equal to 360 degree T by T. The ER component is given by I naught L cos theta e to power j omega T minus R by C divided by 2 pi epsilon naught 1 divided by CR square plus 1 divided by j omega R cube. So theta component is given by I naught into L sin theta e to power j omega T minus R by C, where I naught e to power j omega T by R T minus R by C is current, 4 pi epsilon naught j omega C square into R plus 1 by C R square plus 1 divided by j omega R cube. H phi is equal to I naught e to power j omega T minus R by C L sin theta divided by 4 pi and j omega divided by CR plus 1 by R square. In the far field, we have only two field components, E theta and H phi. E theta is given by J I 60 pi sin theta into L divided by R lambda. H phi is equal to J I sin theta into L divided by 2R lambda. Impedance of space is given by E theta divided by H phi, which is equal to magnitude of epsilon naught divided by mu naught divided by epsilon naught, which is equal to 377 ohm. In the low frequency case, we have three components, ER, E theta and H phi. ER is equal to Q naught L cos theta divided by 2 pi epsilon naught into R cube. E theta is Q naught L sin theta divided by 4 pi epsilon naught R cube. H phi is equal to I naught L sin theta divided by 4 pi R square, where I naught is peak value of the current, mu naught is permeability, epsilon naught is permittivity. when the medium is free space. In the table, fields of the short dipole has listed general expression, far field expression, and low frequency case or quasi stationary case. We know that the short dipole consists of a thin conductor of length L with a uniform current I and point charges Q at the both the ends. Then the average Poynting vector is given by S is equal to half real part of magnetic field and electric field. The far field components are E theta and H phi, where ER is negligible, yes. So that radial component of the Poynting vector is given by half of real part of E theta into H phi. Equation 2, where E theta and H phi are complex. The far field components are related by the intrinsic impedance of the medium. Hence, we can say that E theta divided by H phi is equal to Z, or E theta is equal to H phi into Z, which is equal to H phi root of mu naught divided by epsilon naught when the medium is free space. Equation 3. Thus, equation 2 becomes SR equal to half H phi square into Z, which is equal to half H phi square into root of mu naught divided by epsilon naught. The total power radiated is given by P equal to integral of radial component of the Poynting vector over the sphere, which is equal to phi equal to 0 to 2 pi, limit theta equal to 0 to pi, SR is H phi square into root mu naught epsilon naught, and ds is r square sin theta d theta d phi. The far field of the short dipole H phi is equal to I naught beta L sin theta divided by 4 pi r. When we substitute the absolute value of the magnetic field in the radiated power equation, then half into mu naught divided by epsilon naught, okay, then phi is equal to 0 to 2 pi, limit theta equal to 0 to pi, then H phi square I naught square beta square L square sin square theta divided by 4 pi r square into ds. Equation 4. Equation 4 becomes half root mu naught epsilon naught Integral phi equal to 0 to 2 pi, theta equal to 0 to pi, I naught square, beta square, L square divided by 4 pi square R square sin cube theta R square d theta d phi. Therefore, P equal to 1 by 32 root mu naught divided by root of mu naught divided by epsilon naught I naught square beta square L square divided by pi square, phi equal to 0 to 2 pi d phi, theta equal to 0 to pi sin cube theta d theta, which is equal to 1 by 32 root of mu naught epsilon naught I naught square beta square L square divided by pi square. So integration of d phi equal to phi 0 to 2 pi. Next, theta 0 to pi sin cube theta is 3 sin theta minus sin 3 theta divided by 4 d theta. Therefore, radiated power P equal to 1 by 32 root of mu naught divided by epsilon naught I naught square beta square L square divided by pi square into 2 pi. Here 1 by 4 3 sin theta is minus 3 cos theta and sin theta is minus plus cos 3 theta divided by 3. Limit 0 to pi. From the previous line, radiated power is equal to 1 by 16 root mu naught divided by epsilon naught I naught square beta square L square divided by pi 1 by 4 minus 3 cos pi plus cos 3 pi by 3 plus 3 cos 0 minus cos 0, which is equal to 1 by 16 root of mu naught epsilon naught I naught square beta square L square divided by pi 1 by 4 cos pi is minus 1, therefore minus 3 minus 1 by 3 cos 0 is 1 and in the above divided by 1 by 3, so cos 0 is 1 by 3, cos 0 is 1. Okay, now radiated power is equal to 1 by 16 root mu naught epsilon naught I naught square beta square L square divided by pi 1 by 4. Here we will get 16 by 3. Therefore, radiated power is equal to I naught square beta square L square divided by 12 pi. into mu naught epsilon naught into root of mu naught epsilon naught. Equation number 5. Radiated power must be equal to the square of the RMS current I flowing on the dipole times a radiation resistance RR. That is, radiated power root of mu naught epsilon naught I naught square beta square L square divided by 12 pi must be equal to the square root of the RMS value into radiation resistance. From this, I'll get the radiation resistance of the short dipole, that is RR, root of, which is equal to root of mu naught divided by epsilon naught beta square L square divided by 6 pi. For a free space, we know that intrinsic impedance is 120 pi ohm. Therefore, radiation resistance is equal to 120 pi beta square L square divided by 6 pi, which is equal to 120 pi beta is 2 pi by lambda, 2 pi square L square divided by 6 pi lambda square. Therefore, radiation resistance is equal to 80 pi square L square divided by lambda square. Or we can write RR is equal to 80 pi square L suffix lambda square, length of the short dipole in wavelength, or RR is equal to 790 L lambda suffix lambda square. 80 pi square is equal to 790. We have seen the radiation resistance of the short dipole with uniform current, that is 790 L square divided by lambda square. When the current is not uniform, on the dipole, or we can say without end loading, radiated power is equal to mu naught epsilon naught beta square L square divided by 12 pi. When the current is not uniform on the dipole, then we consider the average current, amplitude of the average current on the dipole. That is, then the radiated power must be equal to the RMS current of the radiated power must be equal to the square root of the RMS current into radiation resistance. Therefore, radiation resistance is equal to 790 average current divided by peak value of the current into L divided by lambda square. We know that average current is always half of the peak value. Therefore, radiation resistance is equal to 197 L divided by lambda square, or we can say that it's 197 length of the dipole in wavelength.